This is part 2 of a video demonstration for being able to evaluate transfer beams with stiffness modifiers or by using crack deflection with tributary or global load reactions. In part 1 of this two-part series, we showed how to evaluate a transfer level with multiple transfer beams using transfer or load takedown tributary forces and also global forces from a finite element solution. And the purpose of part 1 was to show how to apply user-defined stiffness modifiers in evaluating the beams. In part 2, we're going to show how to actually calculate the cracked deflection in ADAPT and then design the beams relative to that particular solution. So we're going to use the same model as in part 1. A couple of things to note in this model is in the loading combinations we have a cracked deflection combination. So we want the program to determine the level of cracking, if any, at these beams with the application of the reactions, participating in the loads that might produce moments that exceed the cracking moment for the different nodes in the structure. So we have already obtained the reactions for tributary and for the global FEM run. We're going to create a baseline solution, which means we're just going to solve this particular level without any reactions, just to kind of see where we're at in terms of the cracking of the beams with the load applied only at this level. So let's go ahead and start. We're going to go to analysis and we're going to execute the analysis without reactions. So the program will solve for reinforcement for these load combinations. Now this model also contains support lines and design strips in both directions because we want to have a good idea of what the reinforcement will be within the slab so that we can properly account for that in checking the crack deflection. After we've analyzed the structure, we're going to generate our design cuts, and you can see in the X direction we have design cuts so turn those tributaries off, and we're going to design both sets, X and Y. Okay, we'll design the sections for the floor. This essentially dictates what reinforcement is being designed for these loads that under consideration. Remember, these reactions are not applied for this run, and that's an important distinction between this solution and what we'll show next. So once that's done, we can go back to analysis and we can run the crack deflection check. And before we proceed into actually looking at the cracking, we're going to go ahead and select the default display, and I'll generate the reinforcement output for this run. And you can see, for example, in these beams, we have roughly 9 number 8 bars. So there's not a lot of reinforcement. These are currently being designed as RC. Relatively speaking, there's a lot less reinforcement in this run than what I'll show you here in just a moment. So after we have run the crack deflection, we can produce a deflection result for that particular cracked deflection case. We can select, for example, the uncracked case using iGross and our beam deflection uncracked for this run under deformation Z direction. Let's check beam here, deformation Z, and I'll go back to this view. So the deflection is about 1/4 of an inch. This is the uncracked condition. If we look at the cracked condition for the same case, we actually have to do that using the contours. So let's go back here to slab contours, deformation, and reviewing these contours here. We have 0.22. I'll go ahead and change the contour labeling to every single contour. And you can see there is cracking. This is about 0.31. So we went from 0.22 up to about 0.31 at these interior beams. A more direct way of obtaining those results would be to review the loss of stiffness at the beams. And to do that, we'll go to the View Analysis Results. I'm going to isolate just the beams here. I'll go to a wireframe view and selecting the cracked combination, we can go to Beam Actions and check Reduced Stiffness Ratio. And if I numerically turn on the display for the numbers, we can see we have, roughly 40 to, 60 to 50 to 60%, even a little more for the loss of stiffness. Okay. Remember, this is with only load applied to the slab with no reactions. Let's go back and we're going to rerun this now. We're going to run the same process, but we'll use load takedown. And I'll use the tributary reactions and run through the identical process. We'll go now and design the sections. And then we're going to run the cracked deflection again. And after we run cracked deflection, I'll come back and review the reinforcement. So we'll go back and generate the reinforcement. And you can see at these beams, 50 number 8 bars in these beams, 30 on the perimeter beam. If you turn on the design cut, you can see at the center of that beam, we have about 40 square inches of steel needed at that beam. And just by looking at that amount of steel, we can see what that's going to do to the cracked moment of inertia. It's going to potentially create a cracked moment of inertia that's very, very large as compared to I gross. So looking back at the view analysis results, because there is so much steel being calculated for those beams, and that steel is being driven by minimum requirements and also by the need to meet the strength or the demand moment. The moment at the center of that span is around 3,000 kip feet. So we need a lot of steel to meet that design moment. If we come back and look at the cracked moment of inertia, or the loss of stiffness, which is essentially I effective over I gross, in this case, we'll go back to the cracked deflection combination and reduce stiffness ratio. You can see that these are actually 1. On the outside we have 0.86, and intuitively this doesn't make a lot of sense if we say, well, under these point loads, these beams should be cracking a lot more than when we don't have the point loads, where we were cracking 40, 50, 60%. And the reason you're seeing this type of a result is because there's so much reinforcement. The way that the program applies a bilinear cracked analysis using the Branson's method, the program essentially ends up using I gross as the moment of inertia when we rerun the stiffness for these beams and reanalyze for cracking, and that's just due to the large amount of reinforcement in the beam. And to verify that, you could actually go into the cracked underscore name of file.dfl. This is in the databases folder under the ADO folder, subfolder, and this file essentially contains every design cut in the slab. And in this case, we're looking at that center cut on that center beam. We can see that the applied moment under the cracked combination 1 is around, this is in metric, so this is Newton millimeters. This ultimately ends up being around a moment of around 2,900 kip feet. The cracking moment is shown here for top and bottom. We're concerned about the positive cracking moment. This is positive bending, and this is quite a bit larger than the cracking moment. So if we look at the I gross for the full section, notice that I cracked positive and negative are shown, and the I cracked positive is basically matching I gross, meaning we max it out at I gross. That ultimately ends up leading to an I effective equal to I gross for this section. So that is the amount of rebar is considered in the sense that we're calculating I crack using that in the equation to determine I effective, and that leads to this type of a result um, for the solution. This is not always the case. Sometimes you'll have, less, let's say, more cracking on these beams, but it is a function of the amount of reinforcement necessary for the design of those beams. If you have any questions, please contact us at support@adaptsoft.com.